In this particular lecture, we will be focusing on the deletion of keys in the B tree. And remember, when I'm referring to deletion, I'm not saying that we are going to delete a node. We are rather I'm saying that we are going to delete a particular key in the B tree, because in case of a B tree, each node contains more than one keys. So instead of saying that we are going to delete a node in the tree, we are going for deletion of a particular key in the B tree. And the deletion here is a bit complex, because for example, if we have a B tree which has let's say three, this is one node, right? This is one node which has three keys in it. So it results in 3 plus 1 children of this node, right? So when we delete a particular key from this this node, then we need to remove one child as well. So it's not that simple that if we remove only one key from the from a node, then the task is over. No, it is going to have a cascade effect on the complete formation of the tree. So we need to keep few things in mind and before executing deletion on B trees. Now, when we perform deletion, this task is very important, that we need to ensure that while we search for a key in a B tree, because we will be going from root to down and then maybe to the leaf, right? And we may find the key to be deleted in this node, or maybe we find the key to be deleted in this node, but in any case we will be going from top to down. So while doing so, we need to make sure that any non-root node shall contain at least t keys while we go from up to down, right? So this is a very important point, and I'll be emphasizing on it later. So if the key which is to be deleted in a leaf node, that is quite simple. We simply are going to remove it, because when a key is in the leaf node, and we know that leaf node has no children, so it is not going to have an effect. But we need to make sure that the lower and upper bounds on the number of keys which are supposed to be in the node are met once we have performed deletion. For example, if the minimum number of keys to be stored in a B tree node are 3, and for example if we already have 3 keys in a node, and even if it is a if it is a leaf node, and if we delete this key, then this particular node is violating the minimum number of keys which are to be stored in every node of the B tree. So we need to cater for this problem as well. So there are 4 cases in total. Actually these are numbered as 0, 1, 2 and 3. So in total there are 4. The first case is that we have an empty root. Empty root, I will be shortly doing a dry run over an example. So in an empty root, there is a root, but the root does not contain any value. So it contains, it occupies a memory, but there is no value. So obviously if a node has 0 keys, then it will have 1 child. And if a node has, let's say, 2 keys, then it will have 3 child, right? And if a node has 1 key, then it will have 2 children, right? So obviously if a node is empty and it has no key, so it will have only 1 child. So in this particular case, we remove this empty node, and the only child of the node becomes the new root of the B tree, right. So this is a simple case. Then the case 1 is that if k, which is a key to be deleted, is in node x and x is a leaf node, right, and we know that this node has at least t keys, because the minimum number of keys which a node can have is t minus 1, and the maximum number of keys that a node can have 2t minus 1. Right? So in deletion we will be focusing on minimum number of keys, because this always gets violated in deletion, and while we were inserting nodes in the B tree, there our focus was on maximum number of keys. So here if you see that that if the node is a leaf node and it contains t keys, so if we remove a key from this, then it will become t minus 1, which is equal to the minimum number of keys. So this bound is not violated. So we will simply delete the key from the node. Right? Then we have this case 2, and the case 2 says that k, which is a key, is stored in any internal node. It's not a leaf node, it's not the root, it's an internal node. So like if you see here that this k is stored here, and we want to delete is this k, right. So what we do is that we will see that if now if you see here this node, since it's an internal node, it will have one node towards its right and one node towards its left, right. So what we will do, we will see that if the node, first we will see that if this left node has at least t keys, right. So what we will do is we will bring one key from this node, and we will overwrite on this, because this key is supposed to be deleted. So we'll bring this one extra key from here, and we will delete this key. But let's say if now this what I stated, what I just stated is case 2a, right. So we will go to the left child of this k, and we will see that if this left child has at least t keys, so we can borrow one key from here. So we will bring this key and remove this key. Now you may be thinking that why are we simply not deleting this key, right. So because, as I stated earlier, that it's not a simple tree, it's a B tree, and let's suppose if this node has two keys, right, it means that it is going to have 3 children, and once we remove one key from here, we need to remove one child from here as well. So that is why we are not simply removing, we don't want to change the number of keys stored in this internal node. So instead what we do is we simply bring a key from a child and replace it here. So this thing gets deleted and a new key appears here. So we end up having the same number of keys in this particular node, right. So this is done in a recursive manner, right. Like for you do this for this node, then something is going to get deleted from here, so it is going to get borrow a key from the child node, and so on and so forth. So it will work like this. Now just in case if the left child, which is child y, does not have at least t keys, so what should be done? So in case the left child does not has t keys, it means it will have t minus 1 keys, so we cannot borrow from here. So what we will do, we will go to the right child. This is case 2b. So we will go to the right child and we will bring one key from here, and we will replace this key from that. Just in case if the left and right child, both of them have already t minus 1 keys, they are at their minimum, so that case is simple. So what we will do, we will simply remove this key and we will merge these two children, right. So in that case, the one key is getting removed from the parent node, and since we had to decrease one child, so we will be merging these two children, because if you see, um, t minus 1 plus t minus 1 is equal to 2t minus 2, and you can see that ultimately the maximum number of keys by merging these two nodes is not getting violated. So it again becomes 2 2t minus 1, right. So these so I have told you about case 0, case 1, deleting a node in the leaf, and case 2a, case 2b, and case 2c. Now the third case is not specifically about the deletion of any node in the B tree, rather it is about this particular condition, that we have to make sure that while we descend in a tree in search of a key to be deleted, we need to make sure that every node we pass through has at least t keys, right. So now let me read it out. The case 3 says that k, which is a node, k is not the key the key which is to be deleted is not in an internal node, and let Cx be a root of a subtree that must contain k, right. And if k is in the tree, now if Cx has at least t keys, then we can recursively descend into that tree, right, because it contains at least t keys. So the condition which I stated earlier is highlighted, is satisfied. Otherwise, if that node do not have t keys, then we will execute either condition 3a or 3b. Now what is 3a? This 3a says that this node has t minus 1 keys. So and some, rather sorry, this is my mistake, not this node, this node has t minus 1 keys, right. Now, and the key which we are searching for is guaranteed to be somewhere here in this subtree, right. So we need to go down to this tree, but the problem here is that this node does not have at least t keys, right. It has t minus 1 keys. Now if you see this condition, we have to ensure we have to ensure that every non-root node that is considered has at least t keys, right. So this, for this condition, what we will do that we know that if we know that some sibling of this node, in this case this is going to be sibling, has at least t keys, right. It has one key extra. So what we will do, we will move one key from here to its parent, and this parent, the key from this parent is going to be moved here, so it is going to get one extra key. So t minus 1 plus 1 will become t. So then it will have at least t key, and after that we will go down the stairs, right. So this is case A, but in case its sibling does not have at least t keys, what will be that case? Now if you see here, sorry. Now here if you see, the sibling does not have t keys as well, it has t minus 1 keys. So what can be done? So sorry, I'm sorry. So here obviously what we can do is that we will since here we are not going to do deletion because the key which is to be deleted is somewhere here, but while going down we have to make sure that this node has at least t keys. So what we will do, we will bring this key down and we will merge these two siblings. because since we are merging two nodes, it means that one key for in the parent needs also be to be decreased. So this is how it's done. We will merge these two nodes and bring the key from the parent down to the child, to the merged child. So ultimately we will have 2t minus 1 keys here. Now let us consider an example. Consider this t for this b tree to be 3. So it means that at maximum we will have 5 keys in each node, and minimum we will have 2 keys in each node. And of course root is an exception. A root can have less than 2 keys as well, right? So the task here is to delete f. Now first of all we will need to search f. Now if we go from top to down, now this node has t minus less than t minus 1 keys, but it's a root node, so we ignore this. Now while searching for f, we see here we know that f will be somewhere in either in this node or in its children, but before going down we need to make sure that this node has at least t keys, right? So this node has at least t keys. Okay, we can go down, and now in the leaf we find this f, and we know that this is a leaf node, right? And deleting a key from here does not violate this condition, so we are simply going to delete this key from this node, which is case 1, right? Next we are going to, okay, instead of let us do it here so that we can understand. The next task is to delete m. Right. So we have to delete m, right? This deletion we have done. Now in this tree we have to delete m. Now as you see, we will go down from here. Now this is the root node, so no issue, but this is an internal node, and we see that this m is here, right? Now we know that the minimum number of keys a node can have is 2, right? And this m is to be deleted from here. Now we will go to its left child, right? In this left child we know that it has at least t keys, which is 3, which is fine. So the predecessor of m is L. So what we will do, we'll bring this L here, and this we will remove this m from this place, and we will put L here. So this is how this m will be deleted. Now let me make sure that it is exactly like this. So if you see the next slide, the deletion happens exactly like this, right? So the next node which we are going to delete is, let me write here, is, oh sorry I forgot, is G, right? So t is equal to 3, and we have to delete G. We have to delete G from this tree, right? Now if you see here that okay, this G is not here, we can go down. Now G, if you see here, G is here. Now if you see that if its left node does not have at least t keys, because t is 3, so it has t minus 1 keys, and the right of this node also has t minus 1 keys. So this is case 2c, and what we will do, we will merge these two nodes. So these two will become one node, and we will remove G, from here, right? Now as I stated, exactly the deletion has performed in that manner, right? Now the next node which we are going to delete is D, right? Let me write it here, D, and T is equal to 3. Now while going from top to down, this node has less than t keys, we have no issue. Then we come here and we see that this node has while going down, we have to make sure that every node internal node has at least t keys. Now if you see here, this particular node does not have how many keys? Does not have t keys, right? So it means that this is not case 0, this is not case 1, because in case 1 we were looking for the leaves. This is not case 2, the key is not an internal node. This is case 3, right, where we encounter while going down in search of a key to be deleted, we encounter a node where we do not have at least t keys. So what we will do, we will go to its sibling and we will see if the sibling has at least t keys. So the sibling does not have, also has less than t keys. So what we will do, we will merge these two nodes and we will, what we will do, we will put here C and L and T and X and bring P down, right? So this parent node will have no key and it will only have one child. And now as yet we have not performed deletion, right? So and after that we will sorry, this is B. After that we will try to search D. Now if you see here, this is exactly what happens. And then what we can do is once we have done this thing, okay, let me redraw it. Once we have done this, like, okay, let me draw it here, sorry. Once we have done like this, this will be P, it won't be here. Then after that we will be searching for D, and if you see here, after that we will go to this leaf node, and this D, since this node contains already at least t keys, so this D can be removed from this place, right? So this all this these multiple steps have been performed at once in this particular slide. Now before going to any particular deletion, if you see this case 0, which says that if the root is empty, you simply remove that root and make the only child of that root the new root of B tree. So if you see here, this is an empty root, so it will be simply removed, right? Now the final key which we have to delete is B, right? So in this particular, okay, let me write and T is equal to 3, right? So we need to delete B from here. Now if you see here, this node is fine and we know that B is less than C, so we will be going here. And if you see here, B is in this node, so what we can do is we can bring E up, because if we simply remove B from here, so this node already has T minus 1 keys, which is fine, but if we remove this B from here, so it will have T minus 2 keys, which violates the minimum bound. So what we do, we will bring this E from here and replace it with C. So E will come here, because we know that this node has more than T minus 1 keys. And this C, what we will do, we will bring here. So this C will overwrite this B, right? So this is how the deletion of B will be performed. So this is how the final outcome looks like after deleting B. So I hope you have got an adequate idea of the insertion of nodes in a B tree and deletion of nodes in a B tree. What I will suggest, because there is no code which we are going to, although we can code it, and these B trees have been programmed in various languages, but in this particular course we are not going for coding the B tree. So what I suggest is that, for example, this is a sample quiz, so you can dry run by making a B tree of t is equal to 2 and insert all these keys in the B tree, and then you may randomly delete a couple of keys as well, so that you can adequately grasp the idea of B trees, right? So that's it. Thank you.